What up, fam? Let's do use substitution. I've changed the way I've taught this so many times over the years. I think I like the way we've covered it. Now, there's going to be some issues though. Later in the homework, I'm going to tell you to maybe skip in terms of your knowledge for your quiz next class, and then after spring break, we'll come back to it. But when we get to that, I'll show you. Well, actually, I'll show you right now. These guys. So heads up, like we'll deal with these after spring break. We have a full review day with no quiz after spring break. Okay, but everything else besides these four problems, we should be able to do and do it well, because we are going to undo the chain rule. That's what use substitution really is. It's an undoing of the chain rule. And we've already undone the chain rule in Unit 6, where I said, like, okay, we know that the key to the chain rule is like what starts in parentheses stays in parentheses. What starts in the parentheses is that 5x. That's going to stay in the parentheses. I need to take the antiderivative of the outside. Now, this is important. The antiderivative of cosine is just sine. You don't have to do like a square and a 1/2. The antiderivative is sine. What starts in the parentheses stays in the parentheses, but then we need to undo the chain rule's derivative. We have to undo the derivative of the inside. We need a 1/5. And that's it. We can always check if I took the derivative of this. The outside is 1/5 sine. This is always a good thing to do. We get 1/5 cosine parentheses times 5. The 5 and the 1/5 are going to cancel. We just have cosine 5x. It checks out. All right, so we're just undoing the chain rule. We see parentheses, or we don't see parentheses. If we don't see parentheses, they might be there. Take the antiderivative of the outside. What starts in the parentheses stays in the parentheses. The antiderivative of e to the power is e to the power. Okay, plus c. So take the antiderivative of the outside, undo the derivative of the inside. Okay? Take the antiderivative of a negative first power. Be careful. Don't add 1 and multiply by the reciprocal. The power rule doesn't work with the negative first power. The antiderivative would be log absolute. That's the antiderivative of the outside. What starts on the inside stays on the inside, but undo the derivative of the inside. The derivative of the inside is -6. I need to undo that. You could check. If I took the derivative of this, I'd have the derivative of e to the 4x, which is e to the 4x times 4. The 4 and the 1/4 cancel. Boom, I get that. The derivative of this, 1 over 5 minus 6x, times -6, the -6 and the -1/6. So undoing. If I need to take the antiderivative of stuff to the 4th power, I'm going to get stuff to the 5th power times 1/5. That's the antiderivative of the outside, undoing the chain. With one extra thing, we have to undo the derivative of the inside. The derivative of the inside is 4, so I need to undo that with a 1/4. If we have a 3rd power, we first understand that the power rule does work with this negative power. Add 1, multiply by the reciprocal to take the antiderivative of the outside. Undo the derivative of the inside. I need a 1/5. -1/10. 5x minus 6 to the -2nd. I could probably rewrite that. -1 over 10, 5x minus 6 squared plus c. Okay? Now, this next one I like to see before we go into the more undoing of the chain rule is because we have this 3 here. Okay? Just this extra stuff outside. Do we care about the 3? No. It's like, it's just going to be incorporated when I undo the chain rule. And I'll just like worry about it at the end. Okay? So do you take the antiderivative of the 3? No, you ignore it. Because when you work through the undoing of things, you'll just worry about it at the end and just kind of like incorporate it in at the end. This is something to keep in mind when we are undoing what looks like products, but actually is just an undoing of the chain rule. I add 1, multiply by the reciprocal, I take the antiderivative of the outside. I undo the derivative of the inside, I need a negative 1/7. That 3 is still there, we just incorporate it in at the end. We've undone the chain rule, everything kind of comes into play. I get negative 6/7 root 8 minus 7x plus c. Okay, cool. Now, the next 3 are good like, yo, caution, caution, caution. You are going to see parentheses. Parentheses, parentheses. Maybe you see parentheses here. You are going to think I'm going to undo the chain rule here. But it won't work. The one I'm going to point to is this one, and I'll come back to it after doing this one. Okay, so let me come back to those 3 after I do this one. Okay. Now, these are a little bit more complicated because when students see them, they see more than just a chain's derivative. They see this 8x cubed times, and they see product, and they're like, oh, I gotta like undo this product. But what I'm gonna try to tell you is because the derivative of this is this. When I undo the derivative of the inside, I'm gonna be able to cancel the product and just get back to a chain whose derivative is this product. So I'm still going to undo the chain rule like I did the ones on the top. The same way, where like this is just something on the outside that I'm not going to do anything to. I'm going to ignore it. I'm worrying about it at the end. I'm just going to worry about the parentheses first. And I'm going to add 1, multiply by the reciprocal to take the antiderivative of the cube. What starts in parentheses stays in parentheses. But I need to undo the derivative of the inside. Now the derivative of the inside is not just 4, it's 4x cubed. That's the derivative of the inside. I'm going to undo the 4x cubed. I'm going to write it over a little bit. So I got a 1/4 x to the 4th plus 2 to the 4th. Now undo the 4x cubes, the derivative of x to the 4th plus 2. I need a 1/4x cubed. That is undoing the derivative of the inside. Well, this 8x cubed, it's still there. I ignored it, but it's still there. Watch what happens. The product comes from a changed derivative. When I undo that inside's derivative, the x cubes are gone. And it shows me, this is 8/16, which is 1/2, that the derivative of this chain turns into that product. So this is not a product. This is not a product. This is just a chain. But when I take the derivative of this, I get a product. When we focus on the chain and undo the chain, we undo the product naturally, as long as we understand how we have to undo the derivative of the inside. Okay? Now, what do we notice? The x cubes cancel. Undoes the product. If you looked at this guy and did the same technique, this is what would happen. You would probably say, okay, I need 1/3 and a 1/3. I need to undo the derivative of the inside with a 1/2x, but you get 1/6x, x squared plus 1 cubed. This is a product. It's not just a chain. What we want when we undo a chain rule is to start with a chain whose derivative is a product. We have a product, we undo the chain, we undo this product by undoing the chain. I have a chain. When I undo it, I get a product. This is a product of x's times x's. The derivative of this is not x squared plus 1 squared. I'd have to use the product rule. The derivative of the first times the second plus the derivative of the second times the first. You don't remember how to do that. You don't want to do that. This is wrong. So these are just like heads up. Sometimes this technique of undoing chains is not the right approach. Instead, what you need to do is simplify. You need to take x squared plus 1 and square it. Simplify first. Make sure you do it correctly. Then just take the antiderivative of all the different pieces. Don't think of this as like undoing a chain with a square and a 1/2. It won't work out. We can simplify. You can simplify by distributing. Now, x times x is x squared. You need to know what x times x to the 1/2 is. What do we do when we multiply x's? We add the exponents. 1 times a half is 3/2, or 1 plus a half is 3/2. Add 1 multiplied by the reciprocal. Add 1 multiplied by the reciprocal, plus a c. Okay. This, we might think, oh, there's like a chain here, there's parentheses there, but really this is just divide. Divide. X plus 3, the antiderivative. These are not important, but you will see something on your test like that. I think this shows up on your test, almost something exactly like that. So be ready for that. All right, but now let's get to the heart of the matter. Undoing the chain rule, practicing taking antiderivatives, practicing undoing the chain rule. Don't focus on the product, focus on the chain. When we undo the chain, we undo the product, boom. We start with the chain. When you take that derivative, you get a product. Let's see how that works. Antiderive the outside. I need a 1/5 and a 1/5. The 1/5 takes care of the 5. What starts in the parentheses stays in the parentheses. When I take the derivative of this, I'm going to have a negative 3x squared. I don't want that negative 3x squared. I need to undo it with a 1 over negative 3x squared. We ignored the x squared, but it's still there. But the process of undoing the chain undoes the product, leaves us with negative 1/15, 1 minus x cubed to the 5th plus c. This chain's derivative is this product. If you checked, which is always good, you should get what you're looking for, which is multiplying these together, you get the negative 3 and the negative 1/3 cancel. X squared 1 minus x cubed to the 5th. X squared 1 minus x cubed to the, 4th, sorry. To the 4th. Yeah. Okay, so we did it. You could always check. When you start with a chain, you take the derivative, you get a product. For all of these, when you undo the chain, you undo the product. Okay, start with the cosine parentheses. The antiderivative of cosine is just sine parentheses. You don't like add 1 to the parentheses, multiply by the reciprocal. No, the antiderivative of cosine x is sine x. The antiderivative of cosine parentheses is sine parentheses. So I'm going to start with focusing on the chain, undoing the chain. I get sine parentheses. What starts in the parentheses stays in the parentheses. I undo the derivative of the inside. The x's will cancel. I ignored this. I worry about it after I undo the chain, and I get my answer 3/2 sine x squared. Let's see. We got it. Okay? Take the derivative, c. Derivative of sine is cosine x squared times 2x. The 2 and the 2 will cancel, so it'd end up with 3x cosine x squared. Boom, 3x cosine x squared. Here's another antiderivative of sine parentheses is just negative cosine parentheses. You don't add 1 to the power, you don't multiply by the reciprocal, so you just get negative cosine parentheses is the antiderivative of the chain. I'm going to ignore this. It will end up undoing itself when we undo the chain. What starts in the parentheses stays in the parentheses, 4 minus 2x cubed. Undo the derivative of the inside, that's going to be negative 6x squared. So I'm going to have a negative 1 over 6x squared. But that's going to cancel with this negative, so it'd be a positive, so that's important. I already have a negative cosine, and then this is a negative 6, so it's going to be a positive 1 over 6x squared. I'm sure a lot of you will make a mistake on that. The x squared is there. It's still there, but it gets undone, giving me 1/6 cosine. Not a product, a chain whose derivative is a product. If I take the derivative of this, ooh, this is fun. The derivative of the cosine, negative sine. The derivative of the inside, negative 6x squared. The negatives and the negatives will cancel. The x squared stays. The 6 and the 1/6 cancels. Boom, I get positive x squared sine 4 minus 2x cubed. With ease, the power is the parentheses. The antiderivative of e to the power is e to the power. The antiderivative of e to the x cubed will be e to the x cubed, but then we will undo the derivative of the x cubed with a 1 over 3x squared. This x squared I ignored, but it's still there. It will go away with that x squared, giving me a chain whose derivative is a product. Same thing here. This one is fun though. The antiderivative of e to the parentheses is e to the parentheses. So I got e to the, what starts in the parentheses stays inside the parentheses. Now watch how this gets tricky, but we can do it. What is the derivative of the parentheses that we need to undo? Maybe it takes a little more steps. We can't just do it in our minds. We got to think about either using the quotient rule, which all of you forgot, derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared, or rewriting it as 3x to the negative first, whose derivative is negative 3x to the negative second. Now, I need to undo this, negative 3 over x squared. The derivative of this is negative 3 over x squared. If I took the derivative of this, I'd get e to the 3 over x times negative 3 over x squared. How do you undo this is with its reciprocal. It's kind of like when we had roots. When I take the antiderivative of x to the 1/2, I get x to the 3/2. I don't divide by 1 over 3/2. I don't go 1 divided by 3/2. I just multiply by the reciprocal, right? Well, when we have a derivative, that is a quotient. Here's the derivative, that's a quotient. The derivative, that's a quotient. Flip it to undo it. Now, how does that work out? Well, this x squared is still there. If you'd like to rewrite this as like 1 over x squared times e to the 3 over x, boom, that gets undone with that. Gives me negative 1/3 e to the 3 over x plus c. Here I undid a quotient, which you could think of as a product if you have x to the negative second. And honestly, you could, if you wanted to. Here's another option. You could have said x to the negative second, e to the 3 over x. Antiderive the outside, e to the parentheses stays e to the parentheses. The derivative of the inside is negative 3 over negative 3x to the negative second. Watch how I can undo that, negative 3x to the negative second. And you leave the x to the negative second, and you're like, oh yeah, the x to the negative seconds just cancel, and you just get the negative 1/3. That's another option. And I like both options, as long as you figure it out. This part, I'm going to say ignore for now. I'm wondering if I'm making the right decision with this. I think I am. It's less to memorize, but there are some questions that involve what's called changing the bases. I think if we just worry about it at the end, we're going to be fine. Don't worry about it after spring break. We're really going to be fine. Think of it as another like quarter lesson as part of the extra review day. Okay, so I'm going to show you what I mean by changing the bases at the end of this video, where I'm going to do the last part, the extra stuff. Okay? All right. Now we want an answer. I'm asked for the area. I'm asking, like, what is this answer? So let's just remember the fundamental theorem of calculus. Isaac Newton discovered that if you want to do an accumulation of velocity times time, you can find a change in position. Or, this is the fundamental theorem of calculus. If you got an f prime sign, okay, you know f is increasing. How can you find this number? Two ways. You can either just find the area under it using a calculator. If you have a graph, boom, you get this. You get that number. But what's the other way to get this number? Well, if you know what f of a's value is, and you know what f of b's value is, subtract the two. This minus this will also give you that. That's the fundamental theorem of calculus. Now, it doesn't matter if, like, we have a c, because if this is 4 plus c, the c's will cancel, this will be 4. So subtracting two positions gives you a displacement or gives you an area. So our goal here is to take the antiderivative and then plug in 2 and plug in 0 to then find the displacement, which is the area. All right, so antiderivative, focus on the chain, undo the chain, use substitution, undo the chain. I get a 3 and a 1/3. I got x cubed plus 1. I got to undo this derivative. I am going to have a 1 over 3x squared. This x squared, it's still there. It's still there. It's done. It's undone. I get 1/9 x cubed plus 1 cubed plus a c. This is like my position function. This is like f. I need to plug in 2 and 0. Subtract those two f's. We'll get the area. We'll get the displacement. 8 plus 1 is 9. I think we had this very similar. Ooh, I can do this. 1/9 9 cubed minus 1/9 1 cubed. 9 cubed divided by 9 is 9 squared. 9 squared minus 1/9. I'm going to go ahead and do this as 81 minus a 9th like that. Now, what I love doing with these problems is checking using my calculator, where my calculator will use an advanced Riemann sum to find this area. It does a bunch of trapezoids, and it does a bunch of velocity times times. I do not use that approach. I find the change in the antiderivative, fundamental theorem of calculus. Is that nice? Okay. Now, what, we'll go back to change of basis later. E to a power, antiderivative of the outside, undo, the x is still there, x's cancel, I have 1/2 e to the x squared plus c, plugging in 2 and 3, I get 1/2 e to the 9th minus 1/2 e to the 4th. It's fun to check. Math 9, 2 to 3. Your calculator is doing an advanced Riemann sum. We are using antiderivatives. My calculator's advanced Riemann sum gives me 4,024 by antiderivative Newton approach gives me the same answer. Very accurate, and they did it very quickly. They use a very advanced Riemann sum. Okay. Ignore the outside, ignore the product. It will be undone when we undo the chain. It's a 1/3. To undo a 1/3, I need a 4/3 and a 3/4. What starts in the parentheses stays in the parentheses. Undo that derivative, I get a 2x. X will undo the product. Gives me 3/8 x squared plus 7 to the 4/3 plus c. Find the change in those two positions. C won't matter. I get 3/8 8 to the 4/3 minus 3/8 7 to the 4/3. This is unsimplified. I'm not going to check this. All right, before I jump into this one, I'm probably going to rewrite this as stuff to the -1/2 power. Ignore the x. Ignore the x, we'll worry about it later. So add 1, multiply by the reciprocal. What starts in the parentheses stays in the parentheses. Undo the derivative. The x is still there. The x will cancel, undoes the product, the 2's will cancel, undoes that, giving me my antiderivative, the square root of x squared plus 9 plus c. When I find the change, the c won't matter. I get the square root of 16 plus 9 is 25, minus the square root of 9. 5 minus 3 is 2. Well, that's fascinating. I think I'm going to look at this graphically. X over root x squared plus 9. From 0 to 4, I'll go -1 to 5. Doesn't fit. Though I probably, oh, that's good, yep. Second, calc 7, 0, 2, 4. Yo, am I gonna get 2? What? Calculator uses a Riemann sum, I use an antiderivative. You don't see parentheses, you don't see a chain, but it's there. Now, indications of why it's there and why we are undoing a chain is the inside's derivative is the outside. Like the inside's derivative, x squared plus 1, 2x, like I see an x out there. This is why this works and why undoing the chain rule undoes what is a quotient. So, antiderivative of the outside. The Antiderivative of a negative first power, don't try to add 1 and multiply by the reciprocal. That doesn't work. The power rule works for every power except the negative first power. The antiderivative of negative first power is log. Starts in the parentheses, stays in the parentheses. Undo the derivative of the inside. That 2x stays, but it's going to cancel, giving me log x squared plus 1. From 1 to 2. C won't matter. I get log 5 minus log 2. Now, log properties. If you are subtracting 2 logs, it is the same as dividing the numbers inside the log. Why is this the case? It's the same as the idea of x to the 5th over x squared is the same as x to the 5 minus 2. Subtraction, division with exponents works that way. You may have to, at some point, write log 5 minus log 2 is log 5 over 2. And it's you're using your log properties to understand that. Log 5 minus log 2 is the same as log 5 over 2. Okay? Your calculator, using an advanced Riemann sum, can get this answer quickly using a lot of rectangles or trapezoids or whatever it uses. Nobody knows except the people who work at Texas Instruments who program these calculators. Boom. Okay. You don't see the chain, but it's there. It's been there the entire time. This is a derivative of a chain. Undo the chain. Antiderive the outside. What starts in the parentheses stays in the parentheses. Undo the derivative of the inside. The derivative of the inside is negative 12x squared. So I'm going to want a negative 12x squared in a denominator. This 5x squared is still there. But the x squareds will cancel, revealing a chain whose derivative ends up being this quotient. You get 5 negative 12 log 3 minus 8 times 4, 32. 29. Now it's negative 29, but when you take the absolute value of it, it becomes positive 29. The next one becomes the log of 1. The log of 1 is 0, so this is my answer. You could simplify another log property is that this can come up. I don't think I want to do that, but that's the log property. All right, negative 1.403. This is using Mr. Newton's approach. Your calculator has a program that uses an advanced trapezoidal Riemann sum. Using all sorts of fanciness so that it does not have to work too hard to get the answer quickly in some cases. In other cases, like if you use an absolute value, like the Riemann sum it uses kind of fails, which is fun. But we get the same answer. Okay? But like props to whoever programmed this calculator for getting this answer using a Riemann sum quickly. All right, last one. I don't know if this works. X, 4 minus x squared to the negative first. Anti-derive. Log, worry about the x later. Worry about the chain first. Undo the chain. When you undo the chain, you undo the product. Negative 1/2 log 3 minus negative 1/2 log 3. 0. That's fascinating. We must have some negative area and some positive area. That will cancel itself out. Let's look at this one graphically. Negative 1 to 1. Gotta have some negative and some positive area. Yep. See the symmetry? We call this an odd function. Areas under odd functions usually are 0 if you're talking about the same distance. Odds like x cubed. Second calc. Area. Look how it fills it in though for you guys. It accumulates the y's. See how it's like that? A lot of you still have misunderstandings about what area they're finding and what area to find graphically. We'll get that soon. Worry about this later. Let's finish off with these. Okay? Now, pay attention to what's given to you and what you have. Pay attention. So important for like this second semester. What do you have? What do you have? And what's the question? Most of you guys, you see straight lines, you think, oh, I got to find the area. Start finding it. Wait, slow down. Slow down. This is the graph of f. You're asked for integrals of f prime. You might think, oh, I need the area under f prime. You don't have f prime. What to do? Go with the understanding that to find an area under a derivative, to find an area under a derivative, you could find the change in the antiderivative. This minus this equals that. That's the fundamental theorem of calculus. This minus this. Oh, the antiderivative of f prime of 2x. Undo the outside. Take the antiderivative of f prime, it's f. What starts in the parentheses stays in the parentheses. Undo that derivative. This is the antiderivative. Plug in negative 2 And this is something I can figure out, not with area, but with points. I wish I had more of these in lesson 2, homework. F of 4 is -1, f of -4 is 0. This is 0, this is -1, the answer is -1/2. We don't care about the c. If this is 4 plus c and this is 7 plus c, when you subtract, the c's cancel. You just get 3. Okay, fundamental theorem of calculus, so important. The antiderivative of f prime is f. But we got to undo the chain. I need a -1/2, the undone derivative of the inside. This is the antiderivative, maybe with a plus c. I won't need the c, but I do need to plug in 3 and 1. -1/2 f of -5 after plugging in 3. -1/2 f of -1. Subtracting these two even though it's negatives. It's like adding a positive. F of -5 is -2. So this is +1. F of -1. Yo, you got to figure this out. Love how I have this question. This slope is down 1 over 3. If a slope is down 1 over 3, that's the same as being down a third when you go over 1. If I go down a third, I'm at 1 and 1/3. This point right here is at 4/3. You are responsible for finding these values. If it's not obvious, don't guess, don't think it's at 1/2. That one is at 4/3. 4/3, 5/3, 6/3. So I get my answer 2/3 plus 1, 3/3 plus 2/3, 5/3. I gotta put up that chart again. This gives us this. This minus this gives us this. If this is 3 plus c, if this is 7 plus c, subtract the 2, I don't care about the c, I get 4. Now, what do we need to find those positions? We need some sort of position so that we know, like, oh, if this happened to be at 4, this would have to go to 8. So that was the whole known plus displacement. Worry about the chain. To undo this chain, I got f is the antiderivative of f prime. What starts in the parentheses stays in the parentheses, but I need to undo the derivative. When I undo the derivative, it undoes the x. This is the antiderivative. Plug in -1 and 2. You get 1/2 f of 4 minus 1/2 f of 1. F of 4 is -1, so this is -1/2. F of 1 is 0, so this is 0, so this answer is -1/2. This is a good one. I really like this one. Because you don't see it maybe as well as we did in the past. What did we recognize for the ones earlier? These. The derivative of the bottom was in the top, log. The derivative of the bottom was in the top, log. The derivative of the bottom was in the top, log. the derivative of the bottom is in the top log. Maybe it's something you have to recognize. Undoing the derivative of the inside, but that undoes this f prime. Whew, that's a good one. I love this one. And I love this one because we get log of f of 3 minus log of f of negative 3. F of 3 is 0. Oh, I wouldn't ask you this question. You don't know what the log of 0 is, but never mind. F of negative 3, 1, 2, 3 is 2. But that's how you would do it. This can't be done. Probably would change it to f of 4. Yeah, change that to 4. Boom. Change that to a 4. It's log absolute f of 4. I made this homework, so I'm surprised I didn't make any mistakes before that. F of 4 is negative 1. The absolute value of negative 1 is positive 1. My answer is negative log 2. Okay? This is the same thing. The parentheses are there. The antiderivative would be e to the parentheses. What starts in the parentheses stays in the parentheses, but we need to undo the derivative of the inside. This might be easy enough to just recognize that e to the f of x's derivative is e to the f of x times f prime. Mallet. Okay. Don't worry about the c. I get e to the f of 2 minus e to the f of negative 2. Sorry, this is so busy. Oh, I don't even think you can see either. There. Antiderivative, e to the parentheses is e to the parentheses. Undo the derivative of the inside. Whew, look at how that works. F of 2 is 1. F of negative 2 is 5/3. And that's my answer. E to the first minus e to the 5/3. Okay? Okay. Now, let's go back. That's like the end of like day 1 use substitution. Here's day 1.5. Which you're going to worry about after spring break, but I'm going to just finish it up. Okay? We could have done these things a different way. Let me show you. We could have just said, yo, we got to undo that derivative of the inside. I need a 1/5. Okay? Undo the derivative of the inside first, before I worry about taking the antiderivative of that. Cool? So like, not worrying about the outside and the chain yet. We're just going to undo the derivative of the inside. Now watch what's going to happen. I'm going to say, you know what? Don't even pay attention to the inside anymore. I've already undone its derivative. I've taken care of it. Just going to be like, yo, something. It's you. We're undoing things. So it's you. Watch what they want you to do here. If you want this approach, and we'll go back and do like other examples to see how this works and why it's like, oh, cool, this is interesting. We are saying u is equal to the inside of the composition. Well, if I change this from x's to u's, I need to change this to du. Now, what does du mean? It's like a small change in u. It's like a width. This is a small change in x. Well, what I've just done is I've changed bases. I've changed from u's to x's to u's. Now, these two values, 1 and 2, these are x's on an x-axis. What I need, if I go to a u-axis using u's, is to change these to u's using my connection. Now, good. But what else do they want you to do? Realize that this 3/5 can be pulled to the outside, get rid of it, multiply by 5/3. And it's just showing you like equivalents of two different, seemingly different integrals, but they're like super connected / related. This is asked often on the AP test, not often, once or twice on the AP test. And now that I think about it, I don't like it because it's just like annoying and it's an extra little like ticky-tack thing to throw in there. Let me walk through that again. Don't worry about taking antiderivative of the outside. Just worry about the inside. Undo the derivative of the inside. Cancel the stuff you can cancel. Okay? But we're going to completely ignore the inside now. We're just going to replace it with something else, a different variable, u. Since it's using u's, we got du. If we replace 2 minus x squared with u, if x is 1 and x is 2, but I change from an x-axis to a u-axis, I change my bases. 2 minus 1 is 1. 2 minus 4 is -2. Yeah, this is still equal to 6, but since we just worried about undoing the inside, I can divide both sides by -2, and I get -3. And this is what they want you to produce. Let me show you another one. Don't worry about undoing. Just keep the integral. Let's just worry about the inside. Undo the derivative of the inside. Okay? Undo the derivative of the inside. Stuff will cancel. Cool. It's like a different order of operation. Undo the derivative of the inside first. Well, we replace things. We replaced x to the 4th with u. I'm ignoring the x to the 4th. I'm just saying, whatever, it's gone. Now, why would I do this? Just to show equivalence of two different things, and to be tricky. Changes these x's of 0 and 1 to u's of 0 and 1. That's nice. And potentially changes something to be easier to understand or find or something. I don't know. Just shows up. Watch what that means in this problem. Ready? Let's hold on to this. 1/9 x cubed plus 1 to the cubed from 0 to 2. Okay, watch. Ignore the inside. But undo the derivative of the inside. Okay? Undo the derivative of the inside. Ignore this. Worry about this later. Let's just undo the derivative of the inside first. Oops. Take care of the undone first. It's a different order of which to worry about things. Undo the derivative first. Then, if you change this to just u, you can change this to 1 to 9 because you plug in 0 and 2 for x and it changes to u's of 1s and 9s. Watch how you can take the antiderivative of this, plug in 1 and 9, and you get the exact same thing as what we did. It's just how this is done, this u substitution, is in a different order. It's a good way to explain it. Most of you will be like, why would I want to do that? Well, that's how it's like taught, which is less intuitively and more just like procedurally. Let me show you. We already did this one. I'll show you a different one. Let's go in a different order. Let's just undo the derivative of the inside first. Okay? Let's just replace that and not care about that because like it's like a parentheses, right? We never cared about the parentheses. So we just undo the derivative of the inside. And we just thought of this as like a parentheses. U is like a parentheses. If u is x squared, you can change this to 4 to 9. The x's cancel. If I just thought of this as being the parentheses, you could turn this into 1/2 e to the u as the antiderivative. Plugging in 9 and 4, you get that same answer. Changing your bases is necessary if you like to do things in different orders. Let me show you this one. This is a nice one. Different order. Undoing the inside first, worrying about the antiderivative second. Okay. Undo the derivative of the inside first. Let's worry about the antiderivative of the parentheses second. Instead of using parentheses, I'm just going to replace parentheses with a u. Okay? I've undone the derivative of the inside. One thing I'm going to note, though, is I changed my base. So I'm going to change my boundaries. I'm going to go 9 to 25. Plugging in x's, turning them to u's. The antiderivative of just parentheses to the negative 1/2 is parentheses to the 1/2 times 2. Okay, the 1/2 times 2 cancels. This is the antiderivative of the parentheses. Okay, plug in 9, plug in 25. You get the same answer this other way. What we like to do is worry about the parentheses first and then undo the derivative of the inside. This other technique undoes the derivative first and then worries about the parentheses second. That's it. I'm glad I figured that out. So, let me see if we can get this answer a different way. Let's see if we can do the antiderivative first. No, it's like so funny because they don't want you to actually take the antiderivative. They want you to just rewrite the integral. It's like, get the last step if you go in this order. This order is worry about the derivative of the inside first. Undo the derivative of the inside first. Worry about the parentheses last. U is x squared. This changes this to 1 and 4. If u is x squared, 1 squared is 1, 2 squared is 4, 1 to 4. We can pull out the 3/2, multiply both sides by 2/3, multiply both sides by 2/3. An equivalent situation is f of u du equals 4. Does that make sense? I'm not going to quiz you on that until after spring break, but we'll do a couple extra practice ones, and then we will also focus on free response problems. All right, we'll review everything. We'll probably grade our quizzes too. And yeah, we'll take our Unit 9 test on Wednesday after spring break. And then we have 4 lessons in Unit 10, and then we're done with content. Cool. All right, hope you understand this new approach to things. I used to teach a more procedural approach. I think this makes more sense. Hopefully. Good luck out there.